Hey, here's an interesting what if. What if you had two bullets? In this case, I show a red one and a blue one. And what if you were to just drop the red bullet from the height of the barrel of this rifle so it falls to the ground, starting from a state of rest? And then the other bullet, the blue one, was shot out of that rifle. Now, keep in mind in this example that the rifle is pointed so that it's perfectly parallel to the ground, right? It's not angled upward or downward, so the velocity of that blue bullet coming out of the barrel is entirely along the x-axis. Okay, so the question is which one hits the ground first? Now, this is very much like the previous demonstration with the two marbles that I had. The only difference in this case is that the bullet would be traveling much faster than the marble. So it's going to go flying somewhere. Gosh, it's going to go off the screen here. I can't even draw it. But eventually it's going to hit the ground, right? Which one hits the ground first? So if you understand this idea that horizontal and vertical motion are completely independent, it doesn't really matter how large this velocity is. If the red bullet has to fall a distance that we'll just call delta y, and eventually the blue bullet, even though it goes off the screen here, it'll eventually go from the same initial height to the ground, and so it travels the same distance delta y. They both accelerate vertically with the same acceleration, g, acceleration due to gravity. So let's look at the equation about, well, timeout. Let's make two separate columns, x and y. After all, the big idea for this whole unit of study is that motion along the x-axis and y-axis are independent of one another. That's the key feature of our study of motion in 2 dimensions. So, well, let's just make some equations that apply exclusively to motion along the y-axis. Delta y is equal to v initial times time plus 1/2 at squared. There's a similar equation for motion along the horizontal axis. Delta x equals v initial times time plus 1/2 at squared. Okay, but I suppose what I mean here is the initial component of velocity along the x-axis and the amount of acceleration that lies along the x-axis. And in the equation for motion along the y-axis, then I mean v initial pointed vertically, just that component of velocity, and I can change this a to a g. Okay, so even though the blue marble has an initial velocity, it does not point at all in the vertical direction. So its initial vertical velocity is 0. So delta y equals 1/2 gt squared. So time is equal to 2 times the square root of delta y divided by g. For both of the bullets, the red one and the blue one, there's no horizontal acceleration. There's no force. Now, of course, the blue one, while it's in the barrel, while it's traveling down the length of the barrel of the rifle, has an acceleration. But once it exits out the end of the barrel, it no longer has any thrust. And I suppose there's a force back to the left of air resistance, but if we take that as negligible, then there's no acceleration along the x-axis, and then the motion horizontally for these two bullets is very different. The red one has 0 velocity, and so it just falls straight down. And if so, it takes a time equal to the square root of 2 delta y over g to hit the ground. And the one that was launched with the initial horizontal velocity spends that same amount of time in the air, but it just happens to have a large velocity to couple with that amount of time that it spends in the air. So some people would argue that they just don't believe it. They find it hard to believe that both the red bullet and the blue bullet spend the same time in the air, because after all, the blue one has to travel so far. So how could something that has to travel so far spend the same amount of time as something that doesn't travel far at all? And I would just argue in reverse, no. The reason they do both spend the same time in the air, and the only reason the blue one travels so far is because it has such a large velocity to multiply by that equivalent amount of time, okay? So let's generalize this type of motion. Whenever an object has a velocity that's applied in the horizontal direction, it travels a path that takes the shape of half of a parabola. So you'll do an experiment in this unit of study at home where you'll roll a marble or a small ball off of a desk. And as that marble rolls along and reaches the edge of the desk, the velocity that it projects off the desk with will be entirely in the horizontal direction. So provided you know the height and the initial speed, then the question at hand is, can you figure out, well, mainly, can you figure out how far away it will land? We'll refer to that as the quote-unquote range of the projectile. So we can call that delta x, we can call it capital R, we can call it d, whatever symbol we want to give to it. It's just the horizontal displacement from the base of the desk to wherever it makes impact along the ground. And there's a few other quantities that you should be able to solve for, right? So you're just given two quantities, one speed and two height. Now height is a direct measurement. All you would need is a meter stick. To measure the speed, maybe you could make two marks across the top of the desk. And then if the ball rolls from A to B, and you have a stopwatch, and so you can measure the amount of time it takes to move from A to B. If you know the distance between those 2 points, okay, so maybe let's do this. Let's reserve the symbol R to represent range, and we'll reserve the symbol D to represent a distance across the desktop. So if you just divide that distance by this time, then you have the initial velocity. So you can't quite measure it directly, but you could do a simple computation to figure out. The idea being that whatever speed it has between point A and B, it maintains beyond point B all the way until it leaves the edge of the desk. And this is true of rolling friction. Sliding friction slows things down, but when a hard marble rolls across a desktop, there's a resistive force known as rolling friction, which is very negligible. So whatever speed it has at any given point across the desk is going to be very much the same. So it maintains that speed until it reaches the very edge of the desk. Right, so this is half a parabola. And from these two given known quantities of velocity and height, can you determine the range? Can you determine the time of flight? Ooh, here's another thing. Would you be able to determine the angle of impact? So if we put a symbol theta right here to represent how many degrees below the horizon the object's velocity vector is pointing, could you determine all of those? You should be able to. Let's go through that. So we've got the same diagram shown again, and here's something like a marble. This doesn't have to be a marble rolling off a desk. If you want to imagine maybe a stunt person, hops in a pickup truck. I always say pickup truck because it's easier to draw than a car. There we go. And then this is just some big tall cliff, and they're going to go driving off the cliff. I don't know, they jump out of the car, have a parachute, or land on a safety net, whatever it is, right? You've seen that scene in countless movies of the car driving off the cliff, right? How far away would it crash into the ground below? And the same question is, how far away is the marble going to land in your next lab? So let's draw a little dot that represents the marble in the air when it's first projected off of the desktop, and we'll show that its speed points in a particular direction. And so it's no longer just a speed, this is now a velocity, right? And if we really do ignore air resistance, say that's a negligible amount of force, then when the marble gets to this point, or this point, or this point, or just before it hits the ground, since there's no forces acting along the x-axis, there's only a force of gravity pulling downward along the y-axis, then the marble always wants to keep the same magnitude of that velocity. So the way I show that the magnitude of the velocity isn't changing, I keep drawing these arrows of the same length. Okay, if I drew the arrow shorter, that would be my way of saying that the speed is decreasing. If I draw the arrow longer, that's my way of saying the speed increases. And because I'm pointing the arrows directly to the right in each case, I'm saying this is just the horizontal component to the velocity. So In this one, I've drawn the subscript 0 to say initially, and then in the rest of them, I'll just say Vx. But the point I want you to notice here is that this horizontal component to the motion, v subscript x, all the vectors maintain the same length. And so there's nothing to change the speed. There is an acceleration here, but that acceleration only acts along the y-axis. In fact, let's take a look at that. Motion along the x and the y-axis are independent. There's another equation of motion we can apply to the y-axis that says final velocity equals initial velocity plus acceleration times time. We can actually apply that same equation to both horizontal and vertical motion. Now the difference here is that the horizontal speed at any given point is equal to the initial horizontal speed plus horizontal acceleration times time. But there is no horizontal acceleration, and so the final horizontal velocity at any instant equals the initial horizontal velocity. That's what I mean by drawing all these vectors repeatedly of the same length. Vertically, the final vertical velocity equals the initial vertical velocity plus g times t. Now the initial vertical velocity is 0. There is an initial velocity, but it does not point in the vertical direction. So at any given point in time, the vertical component to the velocity is increasing by 9.8 meters per second for each second in the air. So 1 second later, the speed is up to 9.8 meters per second in the downward direction. And 2 seconds later, it's up to 19.6 meters per second, and so on and so on and so on, okay? In fact, finally, just before it impacts the ground, the vertical velocity is much larger in magnitude than the horizontal velocity, which might give you the impression that it's almost entirely moving straight down, but no object that's projected off of a flat surface like this will ever be moving entirely straight downward. It's always going to maintain this sideways drift, this horizontal component to the speed. So v initial y equals 0, but then at any other given instant in time, vy is becoming longer and longer and longer. So this is what we have. One component of velocity that maintains the same magnitude and another component of velocity that continues to grow. And the result of that is that the overall velocity is those two motions combined at once. Now, one way we can combine two motions at once is doing something known as graphical vector addition. And one way that we can add vectors together, if we have a downward vector added with a horizontal vector, we make a parallelogram. So create a dashed line that runs parallel to Vx, and then we'll create a dashed line that goes parallel to Vy, and from that we've made this red rectangle, and the overall velocity, here I'll do that in green, the overall velocity then is the single vector that bisects this parallelogram. And so we don't label that either Vx or V subscript y, we just label that V. And so we can do that same process again at this point. What's the overall velocity a little bit later in time? And so we can see the result is it starts pointing less and less to the right and more downward. And in fact, if we make that parallelogram in the final case at the instant just before it contacts the ground, then we notice that the overall velocity is directed down at an angle about like that. In fact, we can label that angle of impact. Let's see, well, I actually have two similar right triangles in here, don't I? That's a right triangle, and that's a right triangle. So how about I do one in blue? You see this right triangle at impact. And we'll draw the other one in orange. Okay, knowing what you know about alternate interior angles, this angle theta below a horizontal line is the same as this angle theta above this horizontal line. SOHCAHTOA. sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent to TOA equals opposite over adjacent. So let's look at the blue triangle. We say the tangent of that angle that we've identified is equal to, now what lies opposite this angle? That's a vector that represents the vertical component of speed at impact. And what lies adjacent to that angle theta? That's the constant value of the horizontal velocity component. Okay, well, keep in mind that would likely be one of the given quantities, so we would know this value just based on the setup of the problem, but we don't know the vertical speed at impact. Well, we kind of do, right? Let's see if we can figure that out. So first of all, time of flight. So we stated earlier that the time of flight is the same whether this marble goes flying off the edge of the cliff with a large velocity or it was just barely bumped and fell basically straight down. Just knowing what the height is, I think we've been calling this delta y. How about we change that notation to h? So it's a reminder that it's the height of a cliff. Then isn't the time just equal to the square root of 2h over g? Remember where that comes from? Delta y equals v initial in the y direction plus 1/2 at squared, and we change the a to a g. This is v initial times time. But even though there's an initial velocity, it's only horizontal. There is 0 vertical initial velocity. And we're changing our terminology from delta y into h. So if h equals 1/2 gt squared, it's pretty easy to show that t is the square root of 2h over g. So then if we want to find the vertical speed at impact, it should be equal to the initial vertical speed plus gt. The initial vertical speed is 0, so the final vertical speed at impact is equal to g times the square root of 2h over g. Right? I've just substituted for time this expression. I can think of g as the square root of g squared, so then I can put everything underneath one radical sign, and I have, well, that g cancels with that. Oh, I can just get the square root of 2gh. Maybe I went about this the long way, right? I think I could have used the kinematics equation that says the final velocity when squared equals the initial velocity squared plus 2a delta y. We change the a to a g, we change the delta y to an h, and we note that the initial vertical component to the velocity is 0. So just taking the square root of both sides of the equation shows us that the vertical speed at impact is the square root of 2gh. So it's nice to see that two different kinematics approaches lead to the same result. So in problems of this nature, where an object is projected horizontally from some height, provided we know the height and we know the initial horizontal velocity, and given those two quantities, we can find A, the time of flight, square root of 2h over g. B, we can find the vertical speed at impact, the square root of 2gh. And C, we can find the angle of impact. Theta equals the inverse tangent of Vy divided by V initial x, where, by the way, this Vy is first found using this formula. There's one last thing we said we'd like to be able to solve for. Capital R, the range of the projectile. Well, let's see. For that, since that's a horizontal measurement, we need to use a kinematics equation for horizontal motion. So treating motion along the x-axis as separate from motion along the y-axis, delta x should equal v initial in the x direction times time plus 1/2 at squared. Now watch this. See, We can replace the a with g, and no, we can't. Now, why can't we replace the a with g? Isn't there an acceleration due to gravity? There is, but that's not an acceleration along the horizontal axis. That's only an acceleration along the vertical axis. So in fact, this is a subscript x, which itself is 0, so this whole term goes to 0. So this is just the dirt equation, distance equals rate times time, okay? So that's the formula we use for finding the range. The range is equal to v naught x. Now I'm not going to say times t, I'm going to say times the square root of, yeah, you guessed it, times square root of 2h over g. So see, all you need to know is the initial horizontal velocity and the height, and of course g is a constant, so just given those two quantities you can find range, you can find angle of impact, you can find vertical speed of impact, and you can find time of flight. Why limit ourselves, by the way, to knowing just the vertical component to the speed as indicated by this purple vector? Right? Oops, that's not an initial, it's a final, Vy. Maybe we're more interested in what is the overall velocity, just v, okay? So there's this horizontal component to the speed that was always there throughout the whole flight, never changed. Same here as it is here as it is here. So how do I get the total velocity? Again, if I'm using this parallelogram method of adding vectors, then the overall velocity is just the bisector of this rectangle. So whether I'm looking at this right triangle or the other one that's similar to it, finding the overall velocity is really representative of finding the length of the hypotenuse of a right triangle. So in that case, we would just use Pythagorean theorem. So I guess there's a fifth quantity we could solve for in problems like this. Not just the time or the vertical component of speed or the angle of impact or the range, but we can find the overall velocity at impact or overall speed at impact. I guess when I state the speed and along with it I state this angle, now I'm giving you the velocity. So let's just figure the speed, just the magnitude. So this quantity v is the hypotenuse of a right triangle made up of sides equal to Vy and V naught x. So what? V squared is equal to the square root of V naught x squared plus Vy squared. Oh, and, oh, wait a minute, but Vy is the square root of 2gh, which means Vy squared is 2gh. So we could say that the total speed squared is equal to the square root of the initial horizontal speed, one of our given quantities, plus 2gh. Okay. Well, I take that back. There we go. Sorry, I got ahead of myself with my algebraic work. Pythagorean theorem. V squared, the length of the hypotenuse, is equal to V naught x squared, the length of the adjacent side squared, plus the length of the other side squared. But this we've got right. Vy is rad 2gh, so Vy squared is 2gh. So we're just restating this equation here. So of course, if I then want v, then I can take the square root of both sides. So the total speed at impact is the square root of V naught x squared plus 2gh. That's a lot, right? We can find out 5 other quantities, a through e, given just these 2 quantities of initial speed and height. So in the next lesson, we'll see what things we could figure out in the case where something follows instead of half a parabola, a full parabola. So this would be exemplified in the case of kicking a soccer ball. Okay, so there's your foot, and you kick the ball with a speed represented by the length of this vector, and then at an angle above the horizon. And the ultimate path this follows is parabolic. It spends an equal amount of time rising as it does falling, provided the ground it's kicked across is perfectly level, so it returns and impacts the ground at the same height that it was kicked from. So the same argument is going to be made in a case like this, where the horizontal velocity remains constant throughout the flight, and in the end, we'll see not only can we determine the range of the projectile, but we can also figure out what would be the maximum height reached above the ground level, what's the total time of flight. In this case, it's probably not a surprise that the angle of impact when it hits the ground is the same angle that it left the ground with. But I'm getting ahead of myself, and we'll cover this in detail in the next lecture. Before we get to that, I'll provide an example problem or two where we'll make calculations trying to solve for these quantities. So we'll put some numbers to a problem like this. Okay, well, thanks for tuning in.